Was your I hope everybody had a good time. Did anybody do anything exciting? You can put your hand up. If not, I understand it was kind of to me it was kind of quick. I hope everybody had a good Easter Sunday yesterday too. So all right, so a few things have come up, and I want you all to be aware. Since the last time we talked, one of the things we were doing last week is we had a lot of meetings. We were talking about the coronavirus and how to address it and when we'll be able to come back. Right now, some of you have already heard in different counties are actually still on a lockdown until May 15th. So we're still waiting for our chancellor to go. We've already been told we're still going to be doing this TRI, temporary remote instruction, until the end of this month. And how we'll go beyond that is going to be totally up to the chancellor's office and our presidents and all. But right now, as it stands, this is word that came out last week, is that we will not be coming back this semester. We will be totally remote instruction for the semester, and there are some options, for you. I would encourage you to stick around with me. I know some of you are just waiting for this class to get certificates or to graduate. But you're still going to get quality instruction. I'm going to put it that way. And with that, there are options for you. You can hang with me and get through the semester. We'll have fun along the way. It's just going to be a little more creative. We will not be getting into the lab, but there is talk about possibly somebody's coming in late summer, maybe fall, that you could come back and get some lab time in to kind of get a little more of your, practice down. That's still in talks. We were asked for recommendations by our dean, which then again has to go chain command. Anyways, there also is another option, and I am going to take you over to the actual admissions and records website. Let me go ahead and share this with you. And this is just if you choose to do this. It's not that's not saying you have to do this, but if you choose to and you say no, I don't want to do this. I want to go ahead and get an excuse drop. Now, an EW is treated differently on your transcripts than if you actually go ahead and withdraw, and you drop, whether you drop by time or by drop later during the semester. So this is an option. I just want to give you this option. I hope you'll stick with me and we continue on having fun and do this remote instruction. I will tell you about some classes that we're going to be offering in the summer as we go along, and that I just want you to get to your goal, your actually work goal, and also to your life goals as soon as you can. And unfortunately, this coronavirus has hit a lot of people, and it's actually you've probably all been watching the news, and you can see all the numbers that are out there. So I wanted to share that with you. And it's on the admissions and records website of Santa Ana College, and it has a little talk about the coronavirus and what to do if you choose to drop and you don't want to continue on. And this goes for all your classes, not just mine, all your classes. All right. Are there any questions about that? I just stopped the share on it. Any questions about that? Raise hands. You can type into the box and I'll answer and field questions the best I can. All right. Like I said, did anybody do anything exciting over the break? I know a lot of you probably worked, which I remember that, and I was actually working last week too. All right. Questions, thoughts? Okay, let's go ahead and get started. What I want to do now is start talking about computer systems. Let me go ahead and bring that back up. it kind of got shut down when I went into the looking for there we go. All right. All right, so let's get into computers. Now, computers, believe it or not, have been around for quite a few years. It's nothing brand new. For a lot of us, we had computers in cars back in the 80s. One of the first computer systems I actually worked on, and this is basically I had some electrical background and I actually had some electronics background, which made it easy for me. But a car came in and the car actually had wires cut on it. And that's probably one of my biggest, harness wires. There was a harness, it was a 1980 Chevrolet Citation. And they actually had the wires cut on the harness going across the air conditioning compressor. And what the wiring on that compressor actually, across the compressor actually was feeding all the different electronics for the computer. And that was my first introduction to it. I hadn't done any really formal training, so I was coming in on it. But if you got a little bit of electronics behind you, a little bit of electrical knowledge, you can actually, what I say, muddle through it. But with that being said, what I did is I started, and this is back before we had online services like All Data and up-to-date stuff, like that. And it was a brand new vehicle. It was actually a salesman's car, and they had to get it out and running. So I went to, believe it or not, the local library, and that local library had a book on that, electrical book on that particular system. So it fascinated me. And so I went ahead and I, took the book over to the copy machine, copied a bunch of pages out of it. And then I went ahead and I kind of explored a little bit, and I found out these different types of sensors, which made sense because we've had temperature sensors in houses, and we've had temperature sensors and other things. And it was pretty basic for me, and it was a pretty basic system. Now I understand computer systems have evolved over the years. We had some basic ones. And the main goal for the early computers was, of course, fuel economy emissions and to protect that catalytic converter. So anyways, let me go ahead and share this with you and we'll get started on that end of it. But you should be seeing this now, hopefully. And it actually is the brand new book that is out. And on yours, I think it's still chapter 73 on the, actually, the 5th edition. But anyways, here we go. Go ahead and get us going here. All right, so computer, it have been around for a while. And what we're going to be doing on Wednesday, I'm going to start introducing you to CAN systems. We're going to start with some basic computers. Had slow computers on board cars, and I used to call them the Tandy 100s or Ataris. They were very slow computers, but back then we didn't ask that computer to do very much. Right now, we have computers doing thousands of processes in a second. They're doing a lot more work. We use computers for the navigation. We use computers for autonomous vehicles. There's all kinds of processes these computers have to do. But they all start off pretty much the same. We have inputs coming in from different types of sensors, which we're going to be breaking down this week too. And the input sensors are kind of like your senses. You have an input for your body, a touch, smell. Some people don't have smell. Sight. There's different things that actually our inputs. And we used to have, and we've got more sophisticated on our sensors now. It used to be, temperature sensors, RPM sensors. Then we went into load sensors. All these were basic ones. They've changed and evolved over the years. They've gotten better. They've got more robust, but the sensors continue to be added on. One of the sensors that was added on is actually cameras. They started adding cameras on for accident avoidance systems and for navigation and also for your autonomous vehicles. But it all starts off with an input going into a central computer. Now these central computers, and we're going to talk about the basic, and then when we get into our CAN system in a few days, we're going to start talking about how that has actually evolved on. Our computers, again, we start off with just some basic computers, and these basic computers were for just simple strategies. The first computer, first computers were actually there to start with fuel economy. And believe me, we still had carburetors back then, so there was kind of some strange strategies that they used to make them work. But we had an input of a coolant temperature sensor, we had an input of an RPM sensor, and then we would have like a throttle position sensor. So those were some of the first basic things going on. And the first one I worked on was called a C4 system. Let me bring somebody out in. Let's grab them in. Jesus is coming in. So we had basic inputs. And then those inputs would go into a central computer. This central computer, again, like I said, was very slow. We didn't really ask them to do a ton of work. They were to do some basic functions. And one of the primary functions was to save the catalytic converter, because in 1975, and we'll get into our emissions system section later in the semester, but in 1975, they started putting catalytic converters for emissions control. Well, after that, they started noticing some degradation, and they needed to protect that converter. And one of the first things, one of the things they came up with was to put an onboard computer on a car, and then we could better manage the air fuel control and spark. Actually, first it was air fuel control, then it went into later on to spark control. But they started off with inputs going into your central computer, and then it went and did a process. There was different steps going on to it. We had we had it go into memory, so we could can actually have a strategy board on it. So we actually, when it was at a certain load, a certain temperature, it knew this amount of fuel should be added into the carburetor or the fuel injection system. And then it would put an output. These outputs were your carburetor controls. It might be your fuel injectors. Later on, become timing, and then there would be some things that they're not putting on this diagram here. But we also had another thing that went into it that was actually for feedback. So we'll get into the feedback in just a second here. All right, so one of the sensors that is used for position, this is a variable resistance sensor, and it uses a board. So if you look here, and I'm going to go ahead and grab my pen here. But if you look right here, this is one of the basic wiring systems on it. So we would have a 5-volt come in from our computer going right onto a terminal, and normally it would be on the side or on the top, but it would feed this one wire right here. So I should say this resistor. This resistor board, it wasn't a fixed type resistor. Well, it's a fixed resistor, but it was not a barrel type resistor where you're thinking of. It actually had a board with a resistor pile on here. Now, this resistor would actually be wired up to actually a ground. Now, when it went into a ground, early, it was a grounding outside. Later on, they started grounding it back to the computer. And they did that for a pretty cool idea. So this had this going on. You're going, wait a minute. Well, there was another swiper board. This swiper board would come across here off of another terminal. And depending on the position of that throttle position sensor, it would actually go across and make contact on this board and would feed back a position back into the actual computer, and the computer used that for part of its strategy. So this was basically the first, one of the first sensors that were actually put on the vehicle. All right, so I hope. Any questions so far on that, folks? All right. As I see none, I'm going to move on. One of the things that we need to know too about a computer that's very important is that a computer does not understand analog signals. Analog signals are very foreign to a computer. The analog signal, it doesn't, computers only know ones and zeros. And that's basically how you got to think about it. They know on-off signals, ones and zeros, and the communication link is a bunch of ones and zeros. So what we have to do is take this sine wave or analog type signal that we have for some of our speed sensors, some of our, well, our oxygen sensors are sine wave also, and also that throttle position sensor I showed you just a second ago, or that, sweeper type one. It actually is a analog signal. It's not a digital signal. Computers love when they get a digital signal and they can understand them and they can actually process it, and then they can make some kind of deduction on it. Well, to do that, we actually use for the computer, we'll take that analog signal, like the previous signal you just seen, and we'll take that into a analog to digital converter. Now, this analog to digital converter that's inside the computer is there just to take those analog signals. If it doesn't need to do any conversion, it will bypass that converter and just go right into the computer system. So we'll take that sensor like before, and we'll take that and we'll actually convert it to a digital signal. And it's more of a pinpoint versus a sweep. The computers, this is actually an older computer. This is pretty, you don't see capacitors like that on the boards or resistors on. We use actually resistor boards now. We don't use the barrel type ones anymore on the boards. But we'll have a processor inside. The early ones were non-programmable processors, and you actually, if you ever had to had a fault with the computer and you wanted to upgrade it or put new software in it, you couldn't do it. You'd have to take it back to the dealership. They'd hand you another computer, and then they would take that computer and they would send it to a company that actually had the capabilities of programming it. Sometimes they had to unsolder chips to actually put a new type of system into it. This is important, especially for us engine performance people, and this is where some techs get themselves in trouble. I want to warn you, about non-manufacturer programming. On the computers we have nowadays, they are all pretty much programmable. The programmable, what I mean by that is I can, almost like the computer I have at home, I can update the software in it. And it used to be you had to have very sophisticated equipment to do it. Now we have things like called pass-through devices. The pass-through devices actually have the ability to reflash the software. And sometimes on an engine performance area, it is needed. I want to let you know that there are some TSBs, technical service bulletins, that require you to go ahead and reflash the software. And this is it's done day in and day out by dealerships. The dealerships had it originally, and then we went into independents that actually could do it too if they bought the software. The way we do that is we'll get a technical service bulletin that says, hey, to solve this altitude problem on a vehicle, the best thing to do is reflash the software. And you would contact your customer, let them know that it needed an update, just like you would on your Microsoft computer. And you would get their permission, and then you would, and you got to be very careful, follow all the steps when you're doing it. I'm giving you a very simplistic way of doing it. But you would take and get the permission from the customer. You would go onto the manufacturer's website, and you would actually capture onto your laptop or whatever pass-through device you have, and you would actually reflash just like you would on your home computer. You would reflash the customer's computer. Now, this is, like I said, it's done quite a bit. Now, the other thing that I want to warn you about is there are some performance shops that will actually reflash to performance measurements. Now, some of these are, approved by the manufacturer, but some of them are just a performance thing. Now, if you're going to the speedway and you're going to be doing a racing, and that's all that car is going to be for, there's a little bit of a lenience on that. But if you're on the road and you've had your software reflashed and it's not approved, that is a violation of federal law. And I can tell you stories about how that happened. I'll actually tell you a story when we start talking about CAN system. But it can actually get you in prison. Let's put it that way. So be very careful. You think, oh, nobody's going to know. No, anytime somebody taps in their reflashes, there's a code and they can track it down. When you go in to do your smog check, and if you get a pretty sharp smog technician, they will flag it because the computer talks to the ISO system actually talks to the computer, and then it pulls out a script and also pulls out an ID. And if that ID has been changed, then there can actually be, you won't be able to, and it's possible, I'm not saying it'll happen, but it's possible there can be some criminal prosecutions against you and possibly the shop that actually does it too. So just a forewarning. But this is right in front of here is actually what they call a map. And this map tells the is inside the computer, and this is actually from the first day it's actually brought into service. The computer's brought into service, and like I said before, this map actually has all those little pinpoints, at this temperature, at this load, at this speed, the fuel delivery should be this, and the timing should be this. And this is all, from this actual map. And you can actually remap these with some software. But again, I want to warn you about that federal law that there's actually in place. All right, so one of the things we need to have, because the computer needs to know a timing sequence. Now, this is an actual, and this is an older system too. And this system actually has a clock to it. This clock, I thought I had a computer in here. No, I don't have one with me right now. Anyways, this clock actually is the timing sequence. So you have a voltage signal, which is there again, the computer knows on and off. And when it sees how much time that voltage is turned on, it can actually determine, the load, the actual speed. If it doesn't have a clock to it, it's just random numbers throwing out there and it has no idea. So it has an actual input to the computer that tells us how much time that voltage signal was at whatever. This is location. Now, the locations of the PCM, ECM, ECU, there's been different, verbiage, I should say, different types of names or acronyms for computers. The PCM is pretty much what ASC calls them. ASC is, whenever you go take your A8 engine performance test, they'll call a PCM. They won't be calling them a bunch of other things. But one of the things that are, we need to know about computers, they do get warm. And depending on where the computer is at, it may have it in the ducting for the airflow. It may be finned very well, so it can dissipate the actual heat. One of the, and this is back when I was working at a Unical station back in the 80s. I had a vehicle, we had a contract with CHP. Now, CHP had a fleet of Chrysler vehicles, and on their early systems, they had what they called a lean burn system. And basically, it was to control the catalyst and also, air-fuel ratio, and a few other things. Well, they originally, and this was kind of I don't know if anybody was thinking at that time, I think partially they thought with the airflow coming from the air cleaner, hey, that's a good way to get it to keep it cool. Well, the air cleaner was an old style can type air cleaner. And one of the things they had for that system was a heat induct. So it would help with atomized fuel, heating it up a little bit. Well, they mounted the computer right on the air cleaner. And when they did that, they actually created under engine heat, and they would actually cause more heat up on the computer. This caused the computers to overheat and shut down. And there was many times I was escorted onto the 605 freeway with a patrol car to actually rescue some of these cars. Well, I never got credit for this, but this is what my deduction was. Why don't we, take the wiring harness, make it longer, and put it inside the car right next to the air conditioning box? And the captain said, "Can you do it?" And I said, "Yeah, I just got to get some harness pieces like that." So I did one pilot one. I put it inside the car, and I think later on Chrysler took credit for it. But anyways, that was then, me dumb trying to figure things out. But anyways, it did keep them from actually turning off. And some of the patrol cars, believe it or not, were on hot pursuit, and all of a sudden the engine was shut down. It was kind of sad. What can I say? All right, so here is kind of an example of how the computer controls the different outputs. And one of the outputs that they use quite a bit, and this is actually a power side system. Normally what they do, what is done, strategies on manufacturers is ground controls. They'll use the computer to control the ground. It's a lot less, detrimental to the actual computers. When you do a high side control, it can actually be an issue on some of the transistors inside the computers. Well, this is a fuel pump circuit. As you can see down here, we have a fuel pump, and this fuel pump right down here is being controlled by the computer. And what they'll do for the strategy from the PCM here is they'll actually, when you turn the key on, there's about a 20-second exciting circuit. So for about 20 seconds, it will actually ground, I should say, add power, allow power to flow through this transistor. This is a transistor down here. And this transistor will actually allow power to come through, which will turn this coil on, which will turn that switch on. Again, relays are used to control a higher amperage flow with a lower amperage. So this is going to be your lower amperage side, and it actually allows that circuit to close and to turn on that fuel pump. So it's going to energize that fuel pump, cause pressure to go up onto the rail, and then you'll start cranking the engine over. And after the PCM actually sees an input RPM signal, it'll say, okay, will keep the power on it. You can do that ground side wise too. I just control this side and put it a grounding side, or either or. And you'll use primarily the grounding side and allow power to be on that relay all the time. Anyways, if it doesn't see an RPM signal at the computer, and this is one of your diagnostic routines you need to do, whenever you have a car that doesn't start and you suspect it might have a fuel related problem and the relay is not being energized on, what I like to do is grab a scan tool and see if I have an RPM signal. And depending on what kind of system you have, a manufacturer and all, you may have a fuel pump commanded on or a power to the fuel pump actually signal. So this is one of the things you can do for a no start type situation. So this is just basic. And it gets a little more complicated as we go along. We'll talk more about that as we get farther into our diagnostic end of it. But basically, there's a little control circuit, and actually goes through and it controls simple. This is kind of simplistic again. There's other things that need to be seen. A lot of your fuel pump circuits need to see fuel pressure. Need to see oil pressure and RPM for them to do anything. And if the TPSC is full, all wide open throttle, it will shut off the relay also. So there's different things that we need to look at when we start going into diagnosing our circuits on our computer systems. All right. All right, let's go forward. All right, so here's a different one. Like I said, we can do it different ways. This is a grounding side versus the power side. And like I said, normally your injectors are actually powered up. Fuel injectors are powered up, and then your control is going to be on the ground side. It makes it a little more easier for on the computer, and it doesn't put as much of a load. And we really look at that because, again, I'm going to probably repeat this all the way through the semester. The computer, electronics and computers do not like heat, and they do not like heavy loads. If they see either one of them, you can actually take out little drivers. And these drivers are pretty much, are going to be your diodes and your transistors and stuff like that inside. So again, same thing as we did for the power side versus the ground side. And we're actually controlling it here. And how we control different things, I should say different components or different outputs. Remember, we had an input from the sensors going into the computer, and then the computer takes in and it goes to an output. This output is controlled digitally by the computer too. It doesn't do an analog signal on out, it turns on or off. And this is what it's going to do on everything it controls. So injectors are going to be on and off, and also the canister purge for your smog controls are going to be on and off. Your signal going to your timing is going to be an on and off type signal. So all these are going to be on and off. And we do the controls by duty cycle. So for instance, you have a fuel injector that you are controlling with the computer. The computer is not going to widen open the nozzle or anything like that. It's just going to turn that nozzle on for a little more time. And this is done by what they call duty cycle. So we have on and off signals. So it will have, in about a second of time, we'll have that injector on a certain amount of time or off a certain amount of time. So here is my signal on. So here I'm on, and here I am off. Okay, so this is what we're talking about. This is what we're talking, one cycle coming through. How long was that injector turned on versus off? And we'll have duty cycles of 50%, we'll have duty cycles of 30%. It just depends on how much time the injector needed to be put on, depending on what the inputs were for that actual computer, and also the mapping of the computer. And there's just showing, you see here, we got a little more on time versus off time. And we'll go back and forth. So this is almost like a 50-50% and 75% on. So this was probably the car, if this was an injector, probably got goosed pretty hard, and we had to turn on the injector for a lot of period of time. All right, so any questions about that? I want to kind of go into our next little subject, and we're going to be talking about any questions before we go on further. This is just an overview of computers. The next thing I want to kind of touch with you is to start talking about temperature sensors. It's one of the most critical sensors that are on the car. I really want to kind of just start there, and then we'll end our session today after we've done that. And we'll go into the next subject. What I want to talk to you about is on Wednesday, we'll get into a little bit about CAN systems, and we'll start talking about throttle position sensors too. So that is, what we'll be kind of going over different types of sensors as in the next few weeks, going after different diagnostic strategies that will be trying to get you started for. And some of the stuff I'm going to be giving you is going to be definitely from the different tests because I just got through taking my A8 over for my research, and that research was, I was really excited because it actually was almost exactly, well, it was exactly what I'm teaching you now. So this is going to hopefully help you out as we go along. Let's see if I can get my mouse to allow me to share this with you. I don't want to do that. Up here. Okay. And bear with me, folks. All right, he should be able to get a share going now. All right. So temp sensors can be all over the place. Now I just gave you the wrong one. I wanted this guy. And yeah, here we go. All right, so temp sensors are all over the place. Now, one of the most critical temp sensors that are out there is actually our air intake. And anytime we look at the volumetric efficiency of the vehicle, we're looking at the air temperature. And the reason we look at air temperature is because of the density of the air. As we know, when the air is excited or hot or warmed up, the oxygen molecules kind of buzz around and separate themselves. Whereas we have a very cool temperature, or cooler temperature, I should put it that way, then it becomes more dense in oxygen. And that's one of the inputs that we bring into the computer. And this is why we want to do this layered step on this. So you learned a little bit about the basics on computers. Now we're learning a little bit of the inputs. And this is where you're going to be running off to when you start doing your diagnosis. Now, the coolant sensors can be in different locations. They are sometimes hard to get to, sometimes hard to find. But your temperature sensors are going to be a two-wire type sensor. These temperature sensors are thermistors. You've heard of resistors before, but thermistors are a little bit different. And normally with a resistor, if you take a resistor, and you've probably done this in your electrical classes, or if you're going to take electrical classes, you'll hear about this. When you apply voltage to a resistor, it starts off a low resistance, but as the resistor is used, the resistance changes. Resistance starts stepping up because of the heat. Same thing happens with light bulbs and other things out there. Well, with a thermistor, it's got very high resistance on the get-go, and as it warms up, it starts dropping the temperature. So this is different. We use thermistors because they can be a little more precise on temperature. So here is a thermistor. It looks like, and you'll find the coolant temperature sensor in a water jacket someplace, somewhere it has water flow. Now, temperature sensors like intercoolant temperatures are pretty much encapsulated. They take contact temperature off the coolant, and this is important. This is one of the things I always look at if I ever get a coolant sensor fault. And you'll get a code either for high or low, and sometimes there'll be some strategy errors too. Well, if you get a sensor that is not reading correct information in the car, then it may be that the coolant is low. And don't take out of consideration too electrolysis. If there's an electrical coolant inside, electrical electrolysis in the coolant, then you could actually have a miscommunicate. It's causing that temperature sensor to miscommunicate. Let's put it that way. Or it will actually etch it away too. And that thermistor does not work very good in coolant. Had a older Cadillac, and this vehicle actually had an actual coolant sensor, an air temperature sensor, and this actual coolant, the threading on both of them are the same sensors, and the mechanic previously actually put the coolant sensor inside the airflow hole and put the actual airflow sensor in the coolant jacket. And when somebody started up the vehicle, it took and washed away that thermistor. That thermistor is just a little bulb affair, and it actually destroyed it. So it threw off codes for both sides. It threw off, it couldn't understand the temperature, and it couldn't it was open circuit on the water, the coolant itself. So you want to make sure you look at the sensor and make sure it's right for that right part. So the fix was put new sensors in the right holes, and then start the vehicle, clear out all codes. So here is a thermistor, and this is what you normally see on it. This thermistor actually has, it starts off, like I said, very, very high in actual resistance, and it drops on down. You can actually see right here. So this would be very, very hot, okay, and then very, very cold. Okay, so when you look at it a voltage scale wise, your voltage, okay, because we're using voltage drop. So if we take we wire up to our computer here. Okay, so here's, I know I'm a total artist, and if we take that ECM or PCM, I should say, let's do it right, PCM, and we have our 5 volts going out, so that's my 5 volts, and then here's my ground. So, and then we have our thermistor in here. The thermistor, okay, it's kind of like a resistor. That thermistor, so I apply 5 volts to it, and if it goes through the whole dropping process, that dropping process will actually cause that voltage to go down to 0. Well, but because I have this resistor here, it won't drop all the way. So we have a controlled resistance here on because of temperature. So as we start off, if very low voltage, okay, so normally, this is kind of extreme here, but here we have, we're probably running, when a fully warmed up vehicle, something like 0.5 of a volt. So that 0.5 of a volt here, and when the temperature drops, we're actually going to be very high voltage, and it's not uncommon to see close to 4 volts when we first turn on the car. This is how the computer knows what the temperature is. So this is just showing correlation between temperature and what our voltage would be output. So the computer will actually read it as voltage, so it puts the voltage out, and it actually brings back that ground side here. So anyways, the ground side. So that's just a simplistic way we actually control. I should actually get our information in. And we do this not only for coolant temperature sensors, we'll also do it for air charge sensors. We use temp sensors for all kinds of, we have temp sensors in transmissions, we have temp sensors in air conditioning control. There's different types of temp sensors out there. So if you get a good grasp on how temp sensors work, then you'll actually get a very good idea on all the other sensors too. Now, one thing I want to point out, and this is probably one of the easiest ways of diagnosing if it's a temp sensor or not, or a wiring problem, because you can still have wiring problems along the way. If you get a high temp code or a low temp code, if I see a high temp code flag out, the first thing I do is I unplug the coolant sensor. If it goes fully cold, I know I have a possible inside that temp sensor a grounded, or in other words, it bridged somehow inside that sensor, somehow it bridged inside that bulb, short circuited. Then I know that possible could be a actual temp sensor problem. The next thing, if I unplug it, I should see the actual temperature go very, very low. Usually it tells you something like negative 250 degrees or something like that. You ground, and then you take a T-pin and go across, or you take a connector and go across. Be very careful about going across the connectors. I would not. I go back, either back probe or use a special set of pins that would actually do it correctly and not spread the terminals. But go ahead and ground it and see if you get a very, very high temperature. If you do, okay, that wiring circuit seems to be okay, and we can condemn this coolant sensor. Now, if we ground across, if we unplug and it still sees that high, then we know we have a wiring problem. And same thing can happen on the other side too. If you get a very low temperature and then you jumper it and it still says low, we have an open circuit in the wiring. So that's pretty much really quick how I diagnose a high, either they'll tell you a low voltage or high voltage on that particular circuit. All right. And here it shows it again, and this is going to, this is a stepped one. This is typically on Chryslers. They would actually do a stepped type coolant sensor circuit. And this is a way that they program, well, this is the way they wired it up inside the computer. And it would step, goes up to a certain amount of temperature, up to 420 degrees. And somebody's chatting at my, I'm trying to bring up the chat right now, folks. So hang tight with me. Where is my chat? I thought I seen somebody say something. Oh, let's see. Why is my chat not coming up? All right, let me stop share for a second, and we'll come back to it in a minute here. All right, are you going to over the PowerPoint? We can't see it on our screen. Really? Okay, let me see if I can reshare it, because thought I was sharing it. Now, let's see, and it should have been temp sensors. Anybody? You guys see it now? Hopefully. Hopefully.
Yeah, we can see it.
Okay, cool. Did I kind of screw up there? I'm sorry, guys. I thought I hadn't started sharing it, and I guess I didn't want to share for us for that minute. Okay, so we're back at the actual temp sensor. This is a staged one, so it has a certain resistance at a certain way it's wired inside the computer. That's just pretty much, we really don't have to worry it so much. This is where it's staged inside the computer, and your scan tools will convert it for you. So you really don't need to really think too much about it. It's just for knowledge is what we need to say. So right here is what we really worry about. If we get miscommunication, this is where we're going to be diagnosing primarily. You would get a strange set of codes for something like this going failed. And then you would probably have more things going on versus just the coolant sensor going on. So this is how that actually works. If you want to look at how it actually starts off, so very cold again, dropping down, and then when it gets to a bridged point, like 120 degrees, it actually takes the other side of that computer. So the computer is pretty much going to know this. So when it gets to this point, it's going to switch over. All right, so testing, there's different ways of testing. You can test it by the coolant sensor or the temp sensor. Now you notice right down here at this bulb area right here, this bulb area right here, down here, is what I'm talking about. If it's open finned, then it's going to be a temp sensor. If it's closed, like the coolant sensors are, there is only contact with the surface area, not to the hole inside of that bulb affair. So you want to be very careful and very and make sure that you have the right sensor for what you're doing. If you have finned, they gave you the wrong sensor if you're going to coolant. If it's closed off like this, and then you have the wrong sensor for that actual air temp sensor. So just keep that in mind when you're starting to replace parts. I like to look at what I have and see what caused it to fail. One of the things we had problems with back early on is the mounting of the air charge sensor. They would mount some of the air charge sensors inside the intake manifold. And when they did that and there was a backfire through the, maybe a misfire, somebody wired up the, and this is back when we had spark plug wires, maybe we had somebody wire up the spark plug wires wrong and it crossfired and it shot a flame up through the intake. We would have that, the bulb would get damaged doing it. So it was very sensitive because then it still had airflow going across it pretty violently, and it would cause the bulb to break inside. When it breaks, and it throws an open code. So this is something I wanted to point out. You just, when you're taking things apart, look at them, see what may have failed. And when we get into oxygen sensors, air fuel sensors, I'm sorry, we want to really do some inspection as we come across it. Give us some telltale signs of what caused it to fail. And you don't want to put a part in it fail again. So this is one test you can do. You can take across here, but you need to know the temperature of that surface area before you actually, and you're going to go across some specifications for what you're actually, your specifications are acceptable. Again, don't take the specification down to the nitty gritty. You have to, when you're doing resistance tests, you want to make sure you give it a little bit of leadway. Your leads could have some resistance in it and cause that lead to be different than what your specifications are. Usually, a manufacturer will give you between this and this is what your specifications are. All right, close that out. All right, here is another temperature sensor. This is, again, actually driven by the inside of the computer. Now, this is something that they added. This is when they started grounding it back to the computer. Now, originally, it was grounded to the engine block and like that, but later on, they started grounding into the computer itself. This is a feedback. It actually for checking for those opens and shorts. It will, the computer knows what should be at this leg here. So this is one of the different ways of strategies that some of the manufacturers took. And we had some basic ones like the first one I showed you, and they kind of stepped a little bit farther as they went across. And this is more of a digital output versus it's kind of steps, and it gives you that. That previous one showed you some digital part. So this is a different strategy they went. Air charge sensors, like I said before, are going to be your airflow area. So if your acronyms for your coolant temperature sensors are ECT, and try to get used to some of these different types of acronyms, because this is what you're going to go into your ASE testing. Sometimes they don't spell it out. They just say ACT, and sometimes this is IAT. You want to make sure you get these in like that. Definitely, just let's back up one. And it's going to be very, 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 very quick. So here is another spot that the coolant.
Ya estamos a 13, yo creo ya abrieron ahí. Un lente.
Hey, Sherry, I think you need to, somebody needs to mute themselves.
Not me.
Not you. I know. I see your microphone's off. Somebody's got a little bit of kind of traffic in the background. All right. So, anyways, just kind of going over a little bit about where some of the sensors are, and we actually, on top of being a coolant sensor, we can actually have a head temperature sensor, and this is for more of your, not so much your management control. It's more of making sure the engine's up to temperature before some air conditioning systems will come on, and also some of your critical